Hello, my curious friend, and a very warm welcome to Deepfield Channel. Tonight, we are going to delve into something that sounds almost like a paradox. The end of everything. Explained with the serene calm of someone who has all the time in the world to ponder such a subject. We will discuss the heat death of the universe, that incredibly distant moment when every single star will have burned out, every particle will have forgotten its former state, and the entire cosmos will draw its final silent breath. But I promise to try and keep this fascinating topic from keeping you awake. Before we embark on this journey, I would love to know in the comments which corner of the globe you are listening from tonight. And if you are feeling too lazy to type much, just leave a simple hello. It might seem like a small thing, but that little gesture tells YouTube that our space is welcoming and helps us bring more tired minds here to relax with us. If you enjoy our scientific journeys, please leave a like and subscribe. And to those of you who are already part of our community, thank you so very much. If you want to get even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you are, find a really comfortable position. If sleep comes, accept the invitation. Let us begin. There is a moment you have experienced countless times that holds, hidden within it, one of the universe's greatest secrets. You have held a hot cup of tea in your hands on a cold night, felt the warmth slowly migrate through your fingers, and unhurriedly noticed the cup cooling down. If you waited long enough, the tea became lukewarm. If you waited even longer, it grew cold. If you had infinite patience, a moment would arrive when the cup and the surrounding air reached the exact same temperature, and no more heat exchange would occur between them. Everything would be equal. Everything would be still. This mundane process, this silent cooling of a forgotten drink on a table, is governed by the very same law that condemns the entire universe to its ultimate end. The scale is different. The time frame is incomprehensible. But the principle is identical to what you experience every time a winter afternoon chills your coffee. What makes this so captivating is that no one ever had to be taught to accept that tea cools down. It seems obvious, it seems natural. But when you stop to think about it, you realize there is something profoundly strange about this obviousness. Why does heat always flow from the cup to the air and never the other way around? Why doesn't the surrounding air suddenly decide to give all that heat back to the cup and make it boil again? Nothing in physics would forbid this in terms of raw energy. The total amount of energy would remain the same. The air molecules could, in theory, all move in the right direction simultaneously and reheat your tea. But this never happens, and the reason it never happens is the exact same reason the universe is inexorably marching toward its end. There is a widespread myth about the end of the cosmos that is worth debunking right from the start. Many people imagine the end of the universe as a massive explosion, a catastrophic collapse, a sort of mirrored anti-creation of the Big Bang, as if everything that expanded would one day contract back into a single point of fire and violence. This idea even has an elegant name, the Big Crunch. For a long time it was one of cosmologists' favourite theories, but observations gathered over decades point to something quite different. The universe is not slowing down its expansion, as would be necessary for a future gravitational collapse. On the contrary, it is expanding faster and faster, driven by something we call dark energy, a mysterious force that permeates space, and which, honestly, science still understands very poorly. The end awaiting us is not a scream of fire, it is a whisper of cold. Another common misconception is to think of the universe as relatively full, relatively organized, and relatively similar to what we see when we look up on a clear night. But the universe you observe in the starry sky is a minuscule slice of a reality that is almost unbearably vast and almost unbearably empty. The observable universe, that piece which light has had enough time to cross since the beginning of everything to reach our eyes, has a diameter of about 93 billion light-years. This number, spelled out, starts to lose its meaning before you even finish pronouncing it. And within this colossal volume, the matter you know, the matter that forms stars, planets, people, rocks and oceans, accounts for less than 5% of everything that exists. The rest is dark energy and dark matter, things we only detect through their gravitational effects and which remain shrouded in profound mystery. The stars that dot this space are islands of heat and light in an ocean of cold and darkness. Each one is a gigantic nuclear reactor fusing hydrogen into helium in its core, releasing energy in a continuous torrent that warms and illuminates everything around it. The sun that warms us every day converts about 4 million tons of mass into pure energy every second, following the most famous equation in physics, which tells us that mass and energy are two sides of the same coin. And this has been happening for roughly 4.5 billion years and will continue for another 5 billion years before the sun exhausts its hydrogen fuel in the core. But even this dizzying span of time is just a blink of an eye compared to the timescales involved when we talk about the heat death of the universe. The central concept we need to grasp before anything else is the concept of entropy. The word comes from Greek and carries the sense of transformation, change, and evolution. But in the vocabulary of physics, it has taken on a very precise and simultaneously very poetic meaning. Entropy is a measure of disorder, but that does not fully capture what it is. It is better to think of it as a measure of how many different ways a system can arrange itself internally without making any difference to its macroscopic state. Think of a perfectly organized deck of cards with all suits in sequence from ace to king. There is exactly one way for a deck to be organized like that, but if you shuffle that deck, there are countless ways the cards can be distributed in any mixed order. There are far more disordered arrangements than ordered ones, and therefore, when something changes at random, it is overwhelmingly more likely to move toward disorder than toward order. The universe works in the exact same way, but on scales that a deck of cards cannot even begin to suggest. When heat flows from the cup to the air, the energy molecules spread out over a larger space into more possible forms with more available arrangements. The entropy of the system has increased. The heat does not return to the cup because that would require the molecules to spontaneously organize into one of the very few highly ordered arrangements, and the probability of that is so small it can be treated as practically impossible, even if it is not impossible in pure theory. The universe, similarly, marches inexorably toward greater entropy, greater disorder, and greater uniformity. And when it reaches the maximum possible entropy, when there are no more temperature gradients, no differences between one corner and another, when everything is at the same minuscule temperature near absolute zero, then nothing else can happen. No star can shine, no reaction can occur, no thought can be thought. This is the state we call heat death. The second law of thermodynamics, which is the physical law governing all of this, is perhaps the most philosophically weighty law in all of science. It states in essence that the entropy of an isolated system never spontaneously decreases. It can remain the same in ideal reversible processes that never actually exist in practice. But in the reality of our universe, it always increases. Always. Without exception. This asymmetry is the reason time has a direction. You can watch a movie of a glass shattering as it falls to the floor and immediately know whether you are watching the film forward or in reverse. The broken glass does not spontaneously reassemble. The shards do not leap from the floor and reform into an intact glass. That would be a decrease in entropy, and the second law forbids it with a firmness that allows no negotiation. But there is something that must be stated carefully here, because it is a point where many people get confused. The second law says that the entropy of an isolated system does not decrease, and the universe as a whole is, by definition, the most isolated system there is, since there is nothing outside it to interact with. But within the universe, local subsystems can very well decrease their entropy, as long as they increase the entropy of somewhere else in compensation. You yourself are an example of this. Your body is an extraordinarily ordered and complex structure, and to maintain this order, you consume food containing energy stored in organized forms, and you release heat and waste, increasing the entropy of your environment. Life does not violate the second law, it uses it, surfing the wave of the universe's increasing entropy to create temporary islands of extraordinary order. Stars do something similar. They concentrate hydrogen, create nuclear fusion, generate light and heat, and distribute this energy through space. Every star that shines is contributing to the overall increase in the universe's entropy, trading organized fuel for dispersed radiation. And every planet orbiting a star, every ocean that evaporates and rains down again, every life form that is born, grows, and dies. All of this is possible because there is a temperature difference between the warm sun and the cold space. It is in this gradient, this difference, that all the complexity and beauty of the universe exist. When this gradient disappears, when everything is at the same uniformly distributed temperature, the story of the universe will have reached its final point. This leaves hanging a question that will accompany us through the next steps of this journey. If the universe is heading toward total uniformity, toward a death by absolute equality of temperature, where right now is the source of all the difference, all the gradient, all the asymmetry that allows stars to shine, oceans to live, and minds to ponder the very end of the cosmos. The question hung in the air like mist over a lake at dawn. Where is the source of all the difference, of all the gradient that allows the universe to be something rather than nothing, that allows there to be stars and oceans and minds capable of asking about themselves? The answer begins not with equations or the names of physicists, but with a simple image that anyone has ever felt in their own skin. Imagine you wake up in the middle of the night and the house is completely dark. You get up, walk to the kitchen and light a candle. For a moment before your eyes adjust, there is only that small, trembling flame in an ocean of darkness. The candle does not create light out of nothing. It releases energy that was trapped in an organized form, the wax, the hydrocarbons aligned in cohesive molecular structures, and transforms that organization into heat and photons that scatter in all directions. The flame is beautiful precisely because it is undoing something. And when the wax runs out, the flame will go out and the room will return to darkness, but the heat and light will already have spread through the environment, never to be recovered in their original form. The entire universe works like this, on a scale that defies any attempt at complete visualization. But then we ask ourselves the most fundamental question: where did the wax come from? Where did the initial organization come from that is slowly being burned away over billions and billions of years of cosmic history? And here we arrive at an answer that, the more you examine it, seems both inevitable and awe-inspiring. The source of all the gradient, of all the difference that exists in the observable universe, is gravity, not in the everyday sense of a force that keeps us on the ground, but in the deepest cosmological sense. Gravity is the force that created the original asymmetry out of near-perfect uniformity. Shortly after the beginning of the universe, the distribution of matter was extraordinarily homogeneous, with minuscule fluctuations, density variations smaller than 1 part in 100,000 compared to the average. But these microscopic irregularities were enough. Gravity is an attractive and cumulative force, so where there was a tiny bit more matter, it attracted a tiny bit more neighbouring matter, which increased the attraction, which attracted even more matter, in a feedback loop that stretched over hundreds of millions of years. Think of a perfectly flat table, tilted at an angle imperceptible to the human eye. You place a tiny drop of water in the centre, and it sits still for a moment, almost in equilibrium. But the equilibrium is not perfect, and the drop begins to slide very slowly toward the lower side, As it slides, it collects other smaller drops along the way and begins to gain speed and attracts even more, and when it finally reaches the edge of the table, it is a continuous stream of water. The table was the young universe. The imperceptible tilt was the quantum fluctuations. The stream of water was the first stars. When matter collapses under its own gravity, something remarkable happens. Gravitational potential energy, the energy stored in the separation between masses, converts into kinetic heat. The particles fall toward the center, gain speed, collide with other particles, and this energy of motion transforms into temperature. A cloud of cold, dispersed hydrogen, as it collapses, heats its core to temperatures that our brains simply refuse to make concrete. These are temperatures on the scale of millions of degrees in stellar cores, where protons gain enough energy to overcome their mutual electromagnetic repulsion and fuse. And here the laws of physics enter not as abstract decrees, but as descriptions of what actually happens when the world behaves as the world inevitably behaves. The first great law governing all this was formulated not by observing the cosmos, but by studying steam engines in the early 19th century. A young French military engineer named Sadi Carnot, who lived less than 40 years and published only a single work in his lifetime, was the first to realize something that seemed to belong to the mechanics of pistons, but actually described a fundamental constraint of reality. Carnot was trying to understand why steam engines could never be perfect, why there was always wasted heat, why no engine could convert all the energy of combustion into useful work. He realized that work can only be extracted from a flow of heat, and that this flow always goes from hotter to colder. A steam engine works because there is a hot furnace and a cooler environment. Heat flows from the furnace to the environment, and along this downward path of temperature it is possible to capture a fraction of it and turn it into piston movement. But never all of it. There is always loss. There is always dissipation. What Carnot was describing, without yet having the words for it, was what we call the first and second principles of thermodynamics. The first says that energy is neither created nor destroyed, only transformed. It is a principle of conservation, of rigorous cosmic accounting. Every earg of energy that existed in the universe at the beginning still exists now, just in different forms. But the second principle is darker, more philosophical, and in a sense more revealing of the deep nature of time. It says that in any spontaneous process, the total entropy of an isolated system always increases or remains the same. It never decreases. The word entropy was coined by the German physicist Rudolf Clausius in the mid-19th century when he was trying to mathematically formalize Carnot's intuitions. He chose the word deliberately, deriving it from the Greek for transformation, wanting to create a parallel with the word energy, derived from the Greek for activity. But entropy turned out to be something much stranger and richer than a simple technical measure of wasted heat. Ludwig Boltzmann, a generation later, gave entropy a meaning that goes far beyond steam engines. Boltzmann was a man of extraordinary physical insight, and also of an emotional sensitivity that would cause him to suffer deeply upon seeing his ideas rejected by much of the scientific community of his time. He wanted to explain thermodynamics from the microscopic movements of atoms, and to do this he needed to develop a way of thinking about probability and order that would redefine physics forever. Boltzmann realized that entropy is a measure of how many different ways the microscopic parts of a system can be arranged and still produce the same observable macroscopic state. A hot cup of coffee in a cold room has low entropy because the fast-moving molecules are concentrated in one specific place. As the coffee cools, the high-velocity molecules distribute themselves throughout the air in the room, and the number of microstates compatible with that configuration grows enormously. There are so many more ways to have molecules distributed randomly than to have them concentrated that the system inevitably evolves toward distribution, not because there is a force pushing toward chaos, but because chaos is astronomically more probable than order. Boltzmann's famous equation, engraved on his tombstone in Vienna, relates entropy to the logarithm of the number of possible microstates. It is an equation that transforms the concept of disorder into a precise mathematical quantity. But the personal cost of this discovery was high. Boltzmann spent years defending the existence of atoms against physicists who considered atomism an unnecessary hypothesis. The intellectual pressure and isolation contributed to a trajectory of psychological suffering that would lead to his end in September of 1906. Less than a decade later, Jean Perrin's experiments on Brownian motion confirmed atoms so definitively that resistance became untenable. Boltzmann was right about everything, but he did not live to see the complete confirmation of his work. What these two laws together tell us about the universe is this: there is a fixed amount of energy that cannot be created, but there is an irreversible tendency for that energy to become progressively less useful, less capable of doing work, more evenly distributed, and more disordered. And the source of the gradient, the answer to the question with which we open this part of the journey, is that the universe was born in a state of incredibly low entropy. Not because it was hot or dense, although it was both, but because all the mass was distributed almost uniformly, without the large concentrations that constitute high gravitational entropy. This seems counterintuitive the first time you encounter the idea. We tend to think that a cold, dispersed cloud of gas is more disordered than a dense, bright star. But from a gravitational point of view, it is the opposite. When gravity has not yet acted, when matter is spread out evenly, there is still enormous potential for reorganization available. The star that forms from this cloud represents a state of higher gravitational entropy, because the matter has fallen into a gravitational potential well, and this process of collapse released energy in the form of heat and light. The star is, paradoxically, a way for the universe to increase its gravitational entropy while locally creating a structure that appears more organized. The Sun, therefore, is not an exception to the second principle of thermodynamics. It is its most visible local expression for us. Every photon that reaches us is evidence that a certain amount of highly concentrated hydrogen is being transformed into helium and dispersed radiation. The temperature difference between the solar core and interstellar space is the way the universe has found to travel the path from the initial low entropy state to the final high entropy state. And on this path between two extremes, in this slow and majestic descent of a gradient that will take tens of billions of years to exhaust, lies all the time available for stars to form, planets to cool, oceans to accumulate, and life to emerge. Think of a waterfall. The water at the top is in a state of lower gravitational entropy than the water at the base. The process of falling converts potential energy into kinetic energy, and then into heat and turbulence. But halfway down, while the water is falling, it is possible to place a water wheel and extract work. Life on Earth is that water wheel. It does not create energy. It does not violate any laws. It simply takes advantage of the flow that was going to happen anyway. The star was going to dissipate its energy with or without life. Life is just a particularly elaborate mechanism that the universe developed to redirect a small fraction of this flow in extraordinarily complex ways before it disperses definitively. And then we arrive at the local mechanism in action, the most concrete and immediate example available to us. A green leaf on a tree in the garden. It receives photons from the sun, highly concentrated and organized energy coming from a source of extremely high temperature. It uses this energy to build sugar molecules, capturing carbon from the air and incorporating it into organic structures. It releases oxygen as a byproduct and emits low-energy infrared photons in all directions, dissipating more entropy than what arrived on it. The leaf is a local reducer of entropy that increases global entropy, exactly as thermodynamics requires. But the leaf does not exist alone. It belongs to a tree that belongs to a forest that belongs to an ecosystem covering entire continents. Each of these leaves repeats the same process billions of times per second on a planetary scale. And the question that remains planted here, unanswered, is simply this. What happens when this process of capture and dissipation, of building and decay, of flow and redistribution, repeats not billions but trillions of times over intervals of time that our calendars have no categories to name? What the leaf does on a microscopic scale, the planet does on a planetary scale. Every continent that receives sunlight becomes an engine of local entropic construction, organizing matter into increasingly elaborate forms while dissipating energy into increasingly dispersed forms. The question that the previous part planted without answering begins to take shape when we observe what happens between these local engines when they start to interact with each other over vast intervals of time. The first thing that becomes visible when looking at any sufficiently large physical system is that order does not emerge from central planning. No part of the system consulted the other parts before assuming its function. No water molecule discussed with the others the pattern they would form when flowing down a slope. No tree agreed with neighbouring trees on the shape the forest would take when viewed from above, and yet the forest has a shape. The river has a pattern, the ocean current follows a route. This ability that physical systems have to generate organisation without any part intending to organise is one of the most unsettling discoveries of modern science, and it has a name that sounds too simple for what it describes: emergence. Emergence is not magic and it is not mystery, but for a long time it seemed to be both. The physicists and mathematicians who tried to describe it over the centuries ran into a vocabulary problem. The language they had was built to describe parts. Each particle followed simple, well-understood laws. Each molecule obeyed equations that could be written down and verified. But when these parts came together in sufficiently large numbers, something happened that the individual equations could not predict. The property that emerged was not in any of the parts. It was in the relationship between the parts, and that relationship only became visible on a different, broader, more distant scale. Ludwig Boltzmann spent decades trying to build a bridge between the scale of individual molecules and the scale of phenomena we can observe and measure. He understood that heat was motion, that temperature was a statistical average of velocities, that pressure was the result of collisions, but he also intuited that there was something more, that the direction of time, the tendency systems have to always develop in a certain way and never another, was encoded not in the individual molecules but in the counting of their possible states. Entropy, for Boltzmann, was a measure of probability. Systems evolve towards states of higher entropy simply because those states are astronomically more probable. There is an almost inconceivable number of ways to arrange molecules in a disordered state, and only a handful of ways to arrange them in a perfectly ordered state. Time walks toward the most probable, and the most probable is always the most dispersed. But Boltzmann also realized something that deeply disturbed him. If the universe walks inexorably toward equilibrium and maximum dispersion, then how is it that structures exist? How is it that there are stars, planets, forests, oceans with currents, atmospheres with patterns? How is it that, in a universe moving towards statistical chaos, we can look around and see so much pattern, so much form, such sophisticated organization? The answer he developed over his life, and which tormented him until its end, was that these structures are exactly the mechanism by which the universe increases its total entropy. They are not exceptions to the second law of thermodynamics, they are expressions of it. To understand how this idea translates into large-scale patterns, it is useful to observe what happens with a planet's atmosphere. The Earth receives solar energy unevenly. The equator receives much more energy per unit area than the poles. This imbalance creates a temperature gradient, and temperature gradients are stored potential. They are differences that the universe has a statistical interest in eliminating. The atmosphere and the oceans are the mechanism by which this difference equalizes. Heat needs to be transported from the equator to the poles, and this transport creates circulations. Warm air rises near the equator, expands, cools, and descends at higher latitudes. This movement creates convective cells that cover entire bands of the planet. Ocean currents do the same in the liquid medium, transporting heat accumulated in tropical waters toward polar regions, along routes that take centuries to complete a cycle. What is surprising about these patterns is not that they exist, but that they are so stable and recognizable. The Hadley cell, which organizes tropical atmospheric circulation, has existed for billions of years. The trade winds that medieval navigators learned to use had exactly the same origin they have today. These patterns were not created by any agent with an interest in creating them. They emerged from the simple physics of warm fluids trying to move toward equilibrium on a rotating planet. And this is where the rotational factor becomes essential to understanding the shape these patterns take. The Earth's rotation imposes a constraint on how fluids can move on its surface. An object moving in the northern hemisphere is deflected to the right. An object moving in the southern hemisphere is deflected to the left. This effect, called the Coriolis force, after the French mathematician Gaspard Gustave de Coriolis, who described it in formal terms in the 19th century, is not a real force in the Newtonian sense. It is a frame of reference effect, but its consequence is real and visible on any sufficiently large scale. Cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. Ocean currents form large rings called gyres that circulate in opposite directions in the two hemispheres. The geometry of heat distribution on the planet is determined not only by the position of the Sun, but by the combination of that position with the planet's rate and axis of rotation. Coriolis originally formulated his equations to describe the behavior of industrial machinery. He was interested in how rotational motion affects energy transfer in mechanical systems. He was not thinking about planetary atmospheres when he wrote his treatises, but the mathematics was general enough that other scientists, decades later, realized the same equations describe the behavior of winds and currents. This is a recurring pattern in the history of physics. Mathematical tools developed to solve one problem turn out to be applicable to completely different problems, suggesting there are deeper structures beneath superficially distinct phenomena. The observation of large-scale atmospheric and oceanic patterns was for a long time an artisanal project. Sailors noted the directions of the wind and the currents they encountered. Cartographers compiled these notes into maps showing preferred routes for navigation, but it was Matthew Fontaine Maury, a 19th century American naval officer, who first systematized this information in a way that revealed the underlying patterns. He collected the logbooks of thousands of ships and used them to build maps of currents and winds with unprecedented precision. What he revealed was not a set of local peculiarities but a global structure, a circulation system covering all the oceans that had a coherence only visible when all the data was brought together at once. Maury did not have the theory to explain what he was describing. He knew what the patterns were but did not know why they were that way. The explanation would come in parts, over decades, as fluid physics became more sophisticated, and meteorologists and oceanographers began applying Newtonian mechanics and thermodynamics to the behavior of fluids on a planetary scale. What this process revealed was that Maury's patterns were not historical quirks or geographical accidents. They were solutions. The system of currents and winds he mapped was the solution the planet had found to the problem of transporting heat from the equator to the poles as efficiently as physics allowed, while obeying the constraints imposed by rotation and geometry. This idea that natural patterns are solutions to optimization problems proved extraordinarily fruitful. When biologists looked at the structure of leaf veins, they found networks that maximize nutrient transport while minimizing material cost. When geologists looked at the drainage patterns of river basins, They found fractal structures that distribute water runoff as efficiently as possible given the topography. When astrophysicists looked at the large-scale distribution of matter in the universe, they found a web of filaments and nodes reflecting the most efficient way of gravitational collapse given the initial density field. In every case, the observed pattern was the expected pattern if the system had been organizing itself to dissipate energy as efficiently as possible over large intervals of time. This correspondence between observation and theoretical expectation is what makes non-equilibrium thermodynamics one of the most active areas in contemporary physics. Ilya Prigogine, who received the Nobel Prize in Chemistry in the late 70s for his work on dissipative structures, spent decades demonstrating that systems kept far from equilibrium by continuous energy flows spontaneously develop organized structures that would be thermodynamically impossible under equilibrium conditions. He called these structures dissipative because their main function is to dissipate the energy gradient that keeps them existing. They exist because they dissipate. They persist as long as there is a gradient to dissipate, and when the gradient runs out, they disappear. The Belousov-Jabotinsky reaction, which Prigogine frequently used to illustrate his ideas, is a chemical system that, when kept in conditions far from equilibrium, develops spiral patterns that expand and reorganize periodically. No molecule in this system knows it is participating in a spiral. No local chemical reaction has information about the global pattern, but the global pattern exists with a regularity that seems almost intentional. This regularity is not intention, it is consequence. It is what happens when many simple processes interact in a medium that maintains certain conditions for long enough. The galactic scale reproduces this logic in proportions that make any terrestrial analogy seem modest. A spiral galaxy like ours is a system of hundreds of billions of stars, each orbiting a common gravitational center, each emitting radiation, each participating in a flow of matter and energy lasting billions of years. The spiral arms we see in photographs are not rigid structures. They are density waves, regions where matter transiently compresses before continuing its orbit. The spiral shape emerges from the combination of the differential rotation of the galactic disk, which causes regions closer to the center to complete orbits faster than regions further away, and the gravitational perturbations that create and amplify density variations. Here the bridge to the next level of understanding begins to take shape. All the patterns described so far, atmospheric circulations, ocean currents, drainage networks, chemical dissipative structures, galactic spiral arms, share a common characteristic. They are more complex than they would need to be to simply transport energy from a concentrated state to a dispersed state. They have structure on multiple scales. They have hierarchy, with patterns within patterns. They have memory, in the sense that their history influences their present shape. And this additional complexity suggests there is some ingredient beyond simple thermodynamics acting on these systems, some factor that amplifies the complexity that basic physics would produce alone, that creates recursion where there would only be flow, that generates patterns that consult the past to shape the future. The ingredient that remained unnamed is not a new force. It is not an exotic particle discovered in an accelerator. It is not an entity physics had to invent to fill a gap. It was present from the beginning, embedded in the oldest equations describing the behavior of matter, hidden in plain sight within the formalism physicists have used since the 19th century. The ingredient is nonlinearity, and its presence within dissipative systems transforms what would be a simple, predictable flow into something that folds back on itself, that remembers its own history, that generates patterns with far more richness than any external energy source could justify alone. Nonlinearity means, in concrete terms, that the behavior of a system does not scale proportionally with the causes that produce it. In a linear system, doubling the cause doubles the effect. The response is proportional, The map between input and output is a straight line, and this makes the system predictable and, above all, incapable of amplifying itself. Nonlinearity breaks this proportionality. In a nonlinear system, a small perturbation can grow disproportionately because the system responds to its own state in a way that redirects part of the energy flow to feed the perturbation that altered it. The system, in a way, responds to itself, and this self-reference is the heart of what amplifies complexity. To feel the weight of this without losing the thread, think of the surface of a perfectly calm lake. You throw a stone. The impact creates a circular wave that expands, loses energy to the surrounding water, and eventually disappears. The lake returns to equilibrium. This is linearity. The perturbation does not feed back on itself. It finds nothing in the environment to amplify it, and the system dissipates the agitation back to rest. Now imagine the lake has a slightly higher temperature in the center than at the edges, and that this temperature difference causes small waves in the center to gain energy from the thermal difference itself. Now the perturbation does not die. It consumes the temperature difference to grow. The system feeds back on itself. The wave organizes, assumes a stable shape, maintains that shape as long as the temperature gradient feeds it. This is a non-linear system in action, and what has just appeared is a dissipative structure, an order born of flow. The power of non-linearity is directly proportional to the distance from equilibrium at which the system operates. The further from equilibrium, the more energy flows through the system, the more opportunities there are for perturbations to feed back, and the richer the structure that emerges. This creates a hierarchy of complexity that depends on the intensity of the gradient driving the system. Weak gradients produce nearly linear responses, simple structures, predictable behaviors. Moderate gradients produce the first instabilities, the first self-organized patterns. Intense gradients produce structures within structures, nested hierarchies, behaviors that seem almost intentional in their ingenuity. The visible manifestations of this mechanism are everywhere, and one of the most beautiful and accessible is the convection cell, named after the physicist Henri Bénard, who in the late 19th century heated a thin layer of oil from below and discovered that, above a certain temperature difference, the fluid stopped conducting heat uniformly and began organizing into perfectly regular hexagonal cells. Each cell is a ring of hot fluid rising through the center and cold fluid descending at the edges, and the cells fit side by side like a honeycomb that no mind designed. The fluid organized itself because nonlinearity combined with the temperature gradient created an instability that found in cellular circulation a more efficient way to transport heat than simple conduction. The structure emerged because it was thermodynamically advantageous, because it increased the rate of entropy production of the system as a whole. This same hexagonal pattern resurfaces on completely different scales. Solar convection cells, called granules, are on the order of 1,000 kilometers across each, and cover the entire surface of the Sun in an ephemeral pattern that lasts only a few minutes before being replaced by new granules. Viewed from afar, these cells create a grainy texture on the solar photosphere that astronomers call granulation. On a smaller scale, permafrost polygons in the Arctic form hexagons in the frozen ground by the same principle of tension minimization in systems with temperature gradients. The hexagonal geometry is not a coincidence. It emerges independently in systems solving the same problem of dissipating energy efficiently in a two-dimensional space, and finds in this shape the optimal solution repeatedly, in contexts that have nothing in common other than the underlying physics. There are manifestations not just visible but audible of this process. The wind producing sounds as it passes over a string or a chimney is creating a structure called a von Karman vortex street, named after the engineer Theodor von Karman, who mathematically described the phenomenon. When a moving fluid passes around a cylindrical object, The nonlinearity of the flow creates an instability that causes vortices to detach alternately from each side of the cylinder, forming a regular street of eddies that move away in the object's wake. Each vortex shedding creates a pressure oscillation that the air transmits as sound. The frequency of this sound depends on the wind speed and the diameter of the object, and is always the same for a given flow condition. The structure is deterministic, repeatable, and emerges spontaneously from the interaction between the flow and the geometry of the obstacle. Power lines sing in the wind for this reason. Chimneys oscillate. Suspension bridges can resonate with the natural frequency of vortex shedding if they are not designed taking this phenomenon into account, as famously happened with the Tacoma Narrows Bridge in the mid-20th century, which oscillated and collapsed within months of opening for reasons linked precisely to this non-linear dance between wind and structure. The human scale offers other manifestations you have already felt without perhaps having named them. The rhythm of a healthy heart is not metronomically regular. It has a subtle and complex variability that cardiologists call heart rate variability. And this variability is a sign of health because it indicates that the heart's autonomic control system is operating with all its richness of nonlinear feedbacks. A completely regular heart, like a metronome, is paradoxically a sign of disease. It means the complex feedbacks have been simplified, that the system has lost the flexibility that nonlinearity confers. The healthy lung also does not breathe in perfectly identical cycles. The depth and rhythm vary subtly from one cycle to the next, and this variability is maintained by a respiratory control system operating non-linearly, responding to dozens of simultaneous signals from the body's internal environment. Flames are another example you can observe tonight if you light a candle. The flame is not static. It oscillates, pulses, responds to air currents you barely notice, assumes shapes that never repeat exactly. This happens because the flame is a non-linear dissipative structure, operating far from equilibrium, transforming the chemical energy of the fuel into heat and light, and the flow of hot gases it generates creates instabilities that modulate its own shape. The turbulence in the gas flow is also non-linear, and the interaction between the turbulence and the chemical reaction creates the unpredictable dance that makes each flame unique. There is something profoundly poetic in the fact that fire, which the ancients placed at the center of their cosmologies as a symbol of transformation, is precisely one of the most accessible examples of nonlinearity and dissipative structure that everyday experience offers. Nonlinear systems are classified by behavior rather than by composition, and this classification reveals something important about the universality of the phenomenon. Fixed-point systems are those that converge to a single steady state, regardless of initial conditions. A stone rolling to the bottom of a bowl, a damped pendulum coming to rest. Limit cycle systems are those that converge to a stable periodic oscillation. The healthy heart, the mechanical clock, certain oscillatory chemical reactions like the famous Belousov-Zhabotinsky reaction, discovered by Boris Belousov in the 50s, when the Russian chemists noticed that a mixture of citric acid, bromate and color indicator changed from yellow to colorless and back to yellow in regular cycles, something that seemed to violate the second law of thermodynamics, but actually confirmed it magnificently by creating a structure that maximized dissipation. Chaotic systems are those where behavior is sensitive to initial conditions in such a way that nearby trajectories diverge exponentially, making long-term prediction impossible even knowing the exact equations, and even if the system is completely deterministic. We invite you now to notice one of these manifestations in your own experience right now, in this place where your body rests. Your breathing is a biological limit cycle. It oscillates without being perfectly regular, responding to the level of carbon dioxide in the blood, muscle tension, state of alertness. If you pay attention to your breathing without trying to control it, you will notice the cycles are not identical, that some are slightly deeper, others shallower, that the interval between exhaling and inhaling varies. This variability is not noise, it is the signal of a healthy system operating with all its nonlinear complexity. Similarly, the sounds of the environment reaching you now, whether the hum of an appliance, the wind, the silence that is never completely silent, are fluctuation patterns carrying the signature of nonlinear processes, of turbulence on minute scales, of vibrations feeding back within chambers and tubes and structures. What unifies all these manifestations is that they are ordered but not static, complex but not chaotic, to the point of unintelligibility, persistent but dependent on the continuous flow of energy to maintain themselves. Remove the gradient that feeds them and they disappear. A Bernard convection cell vanishes as soon as the heating from below is turned off and the temperature equalizes. A flame goes out when the fuel runs out. The von Karman vortex dissolves as soon as the wind ceases. The heart stops when the metabolism generating the electrochemical gradient needed for the cardiac limit cycle is interrupted. The existence of these structures is as contingent as it seems permanent during the moment we observe them. It is precisely here that the fragility hidden beneath the appearance of solidity begins to appear. We look at a system that seems in equilibrium, that seems to have found a stable shape, that reproduces its patterns with such regularity that we forget this regularity is actively maintained at every instant by the continuous flow of energy through a potential difference that is itself being consumed by the process it sustains. The star warming a planet seems permanent on the scale of a human life. The star warming a planet seems almost permanent on the scale of a civilization, but the star is a gradient, and the gradient is being consumed. And when the gradient smooths out beyond a certain point, the cascade of structures depending on it begins to simplify, each level of organization losing its source of support, each limit cycle losing the amplitude that kept it coherent, each pattern dissolving back into the simpler substrate it was made of. The equilibrium that seems solid is actually a dynamic equilibrium, maintained by the tension between the energy entering and the entropy growing, between the order emerging and the disorder advancing. It is like an acrobat who seems motionless at the top of an impossible balance, but whose muscles are in constant motion, correcting, adjusting, responding. Remove the acrobat's attention, remove the energy source feeding their muscles, and the balance unravels not gradually but suddenly, when the last correction fails and the fall begins. The universe is full of acrobats like this, and thermodynamic physics tells us that all of them, without exception, are on their way to a fall that is mathematically inevitable, only delayed by the temporary exuberance of the gradients that still exist. There is a moment in certain physical systems when the slow and almost imperceptible accumulation of pressure meets a threshold that cannot be crossed gradually. It is like the surface of a frozen lake supporting increasing weight in absolute silence, and then suddenly, in a fraction of a second, cracking into patterns that travel enormous distances before the first sound reaches the ears. The ice was not about to give way uniformly. It was storing tension, redistributing load, delaying the collapse with the very internal geometry that seemed to be its stability. And then the redistribution was not enough, and everything that had been delayed happened all at once. Thermodynamics knows this pattern with disconcerting precision. There is an entire class of phenomena that physicists call phase transitions, and they describe exactly this sudden passage from one state to another when some variable crosses a critical value. Water cooling slowly does not turn to ice gradually. It remains liquid, then liquid still, and then, in an instant, organizes billions of molecules into crystalline structures with a speed that seems impossible for something happening at refrigerator temperature. What changed was not just the temperature. It was the relationship between the temperature and the system's ability to sustain the previous state. The expanding and cooling universe will go through transitions like this. It is not undergoing a smooth decline in all its aspects. It is, in some domains, accumulating the conditions for collapses that, when they happen, will be events of extraordinary magnitude, even if there is no one to observe them. The final heat death is not composed only of growing silence. It is punctuated over timescales that defy any human intuition, by events representing the last releases of gradients that waited eons to dissolve. The first type of intensification worth contemplating is stellar death in its most extreme forms. A star of sufficiently large mass spends its entire life balancing gravity against the radiation pressure generated by nuclear fusion in its core. For millions of years, this balance sustains itself with a stability that seems permanent viewed from any human timescale. But the fuel runs out in layers, each layer requiring higher temperatures to fuse heavier elements, each stage shorter than the last. The star that spent millions of years fusing hydrogen spends only a few thousand fusing helium, then centuries fusing carbon, then years fusing silicon. And then comes iron. Iron is the end of the road for energetically favourable nuclear fusion. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron consumes energy. When the core of a massive star accumulates enough iron, it can no longer generate the pressure needed to sustain itself. The collapse that follows happens in less than a second. The core that was the size of a small city collapses to the size of an even smaller city, with density so extreme that protons and electrons are forced to combine into neutrons. The energy released in this fractions of a second collapse is greater than all the energy the sun will radiate over its entire existence. This energy meets the star's outer layers still falling inward and pushes them outward in an explosion that for a few days can rival an entire galaxy in brightness. This is a supernova, and it is a precise example of what happens when a system that stored gradients for a long time finally reaches the threshold where it can no longer sustain the dynamic equilibrium that defined it. The intensity is not accidental. It is proportional to the duration and depth of the equilibrium that was maintained. The young universe, full of massive stars, was a place of frequent supernovas. The older, colder universe to come will have smaller, longer-lived stars, their deaths quieter, but each death still being the final dissolution of a gradient that lasted billions of years. What remains of a supernova is equally dramatic in the thermodynamic sense. A neutron star is an object where matter has been compressed to densities that do not exist in any other context in the observable universe. A teaspoon of a neutron star material has a mass comparable to an entire mountain. This extreme density is itself a gradient, a concentration of gravitational order that the universe cannot maintain indefinitely. The neutron star will slowly radiate energy, will slow its rotation over immense eons, and eventually will become a cold, inert object spinning in some forgotten corner of a galaxy that also no longer exists in its current form. And then there are black holes, which are the most extreme end of the line of gravitational concentration. A black hole is not an empty place. It is a region where the curvature of space-time has been taken to an extreme that prevents anything, including light, from escaping. The entropy of a black hole, discovered mathematically by Jacob Bekenstein and Stephen Hawking in the 70s and 80s of the last century, is proportional to the area of its event horizon and is vastly greater than the entropy of any equivalent configuration of normal matter. This means a black hole represents paradoxically a state of extremely high entropy, but stored in a way that appears to an outside observer as a concentration of extreme gravitational order. The resolution of this paradox comes from Hawking radiation, a phenomenon operating on timescales that transcend anything else discussed so far. Quantum mechanics predicts that the event horizon of a black hole is not completely stable, that quantum fluctuations in the vacuum near the horizon allow particles to slowly escape, that the black hole loses mass and energy in an extraordinarily slow process, A black hole with the mass of the Sun would take such an incomprehensibly long time to evaporate via Hawking radiation that any number written out in full seems equally absurd, and a supermassive black hole, of the kind inhabiting the centres of galaxies, would take far, far longer. But the crucial point is that the evaporation happens, and when a black hole is in the final stages of its evaporation, when the remaining mass is small and the temperature of the Hawking radiation becomes significant, it releases its remaining energy in a final explosion of extraordinary intensity. The gravitational gradient that was accumulated and preserved for inconceivable eons dissolves in an eruption of photons and other particles that quickly disperse and equilibrate with the increasingly cold background of the universe. This is, in a very real sense, the last form of dramatic event the thermodynamic universe will produce before the final silence. Humanity has developed instruments of impressive sophistication to observe and measure these phenomena on their various scales. Orbiting telescopes capable of detecting gamma rays record supernovas not just in our galaxy, but in galaxies billions of light years away, meaning they are recording events that happened when the universe was a fraction of its current age. Gravitational wave detectors like LIGO capture the ripples in the fabric of space-time generated by the merger of neutron stars and black holes, events that release more energy in fractions of a second than the Sun will release in its entire existence. Each of these observations is a window into a phenomenon of extreme intensity occurring somewhere in the universe at this exact moment, or that occurred and whose signals are still reaching us through space. The astronomers analysing the data from these detectors are, in a profound sense, mapping the thermodynamic calendar of the cosmos, identifying which gradients are collapsing where, with what intensity, following what sequence. The pattern emerging from this mapping is consistent with what thermodynamics predicted: a universe that produces more violent events when larger gradients collapse, and that produces these events with decreasing frequency as the available gradients run out. What is fascinating from a physics point of view is that these high-intensity phenomena are not deviations from the path toward heat death. They are stages of that path. Every supernova is thermodynamics fulfilling its promise with particular exuberance. Every neutron star merger is two gravitational gradients dissolving into a single more uniform state, releasing in the process the difference in the form of gravitational waves and electromagnetic radiation that distribute themselves through the universe and contribute to the overall equilibrium. The universe is not wasting energy in these dramatic events. It is, in them, maximizing entropy in a particularly efficient way. The dynamic structures these events generate have their own thermodynamic beauty. A planetary nebula, the shell of gas expelled by a medium-mass star at the end of its life, represents a pattern of density and temperature that will expand and disperse over tens of thousands of years, but which, while it exists, creates the conditions for the formation of new stars on its periphery. The residue of intensity serves as a seed for the order that will follow. A star-forming region, visible in infrared wavelengths as a field of bright cocoons where gas and dust are collapsing under gravity to ignite new nuclear fusions, is a place where local entropy is temporarily decreasing while global entropy continues to increase. These are the apparent paradoxes that thermodynamics resolves without difficulty. The law governing the increase of entropy never said the entropy of every part of the system must increase at every instant. It said the entropy of the total system must increase. A region can organize, concentrate, structure itself with increasing beauty, as long as somewhere further away entropy increases by at least an equal amount. The stars born from nebulae are exchanges of this kind. The galaxy organizing itself is an exchange of this kind, and the human observer contemplating these structures with wonder is, themselves, an exchange of this kind, a local pocket of extraordinary organization sustained by the dissipation of gradients running in other directions. While you rest, Somewhere in the outer arms of a galaxy whose name does not exist in any human language, a star that spent more time than the Sun has had in total existence slowly fusing its hydrogen has just crossed the threshold where its helium core can no longer sustain the equilibrium that defined it. It is collapsing now, in this instant that has no name for us, because the light from the event will only reach any telescope on a timescale transcending the existence of our species. The collapse will last less than a second. The explosion that follows will be visible in neighbouring galaxies. The elements it forged and dispersed will drift through the interstellar medium for billions of years before participating in any other structure. And this event, so isolated in its apparent singularity, does not actually happen in isolation. The gradients that produced it were shaped by conditions that came from other events, and its dissolution will influence conditions that other systems are still negotiating, with the entropy growing in every direction at the same time. The elements dispersed by that explosion do not meet a vacuum. They meet a medium that already holds the memory of 1,000 previous explosions, a diffuse fabric of gas and dust that scientists call the interstellar medium, and which is not the nothingness the word vacuum suggests, but a living archive of all the stellar deaths that preceded it. Every carbon atom now drifting in this cloud carries a history of fusion, a history of extreme heat, a history of a gradient that existed and dissipated. And upon entering this medium, the newly forged elements do not just exist in it. They disturb it, compress neighbouring regions, create shock waves that travel for thousands of light years and which, upon encountering other clouds in different states of equilibrium, can trigger gravitational collapses that would not have happened without this initial impulse. A stellar death is, therefore, a trigger for births. And each birth is a new cycle of fusion, a new loan taken from the order the universe still conserves, a new bet against entropy that, on a local scale, seems winnable for a few billion years, but which on a universal scale has been lost since the beginning. The most intimate partner of this process is gravity. If thermodynamics is the force dictating the direction of time, gravity is the force creating the conditions for thermodynamics to have work to do. Without gravity, no gas cloud collapses. Without collapse, no star ignites. Without a star, no fusion occurs. Without fusion, no temperature difference exists to be exploited, no gradient forms, no local order emerges from diffuse chaos. Gravity is, in this sense, the involuntary creator of all the complexity the universe has ever displayed. It gathers what expansion and entropy want to separate. It concentrates where everything tends to disperse. And in this tension between gravitating and dispersing, between collapsing and exploding, between local order and growing disorder, the entire history of the visible universe was written. What makes this relationship so fascinating is that gravity and entropy do not oppose each other in a simple way. They negotiate. When a cloud collapses under gravity, its gravitational energy converts into heat, and this heat increases the entropy of the system. When a star explodes, it disseminates energy into increasingly less concentrated forms, further increasing entropy. Gravity, by creating order, paradoxically accelerates the production of disorder. It is the instrument by which the universe consumes its low-entropy inheritance more efficiently. It is as if every structure gravity builds were, from a thermodynamic perspective, just a more elaborate and efficient way to spend the capital of order the universe received at the moment of its birth. This feedback loop between gravity and entropy has cycles manifesting on radically different timescales, and understanding these cycles requires the mind to get used to jumping between orders of magnitude that defy any everyday intuition. In decades, what we can observe is the individual pulse of variable stars, the slow shedding of solar wind, the gradual warming of the sun that in a few 100 million years will make the Earth's surface hospitable only to extremely adapted organisms. In centuries, we will witness the gradual dissolution of some open star clusters, whose members disperse under the cumulative influence of subtle, gravitational encounters that individually are imperceptible, but collectively are inevitable. In millions of years, the configuration of the Milky Way will be unrecognizable in detail. The spiral arms will have reorganized, stars of different populations will have completed entire life and death cycles, and molecular clouds that today exist in silence will be transformed into groups of young stars or dispersed without leaving a visible trace. This behavior across different temporal scales reveals something profound about the nature of the systems that gravity and thermodynamics build together. They are simultaneously predictable in their tendencies and unpredictable in their details. The tendency is clear. Entropy grows, gradients smooth out, local order persists for a while and then dissolves. But the exact path any specific system will take on this journey depends on initial conditions that can never be known with enough precision to eliminate uncertainty in the details. And this sensitivity to initial conditions is not a flaw in our knowledge, a gap that more instruments and more calculations will eventually fill. It is a fundamental characteristic of the systems physicists call chaotic, not in the popular sense of disordered, but in the precise technical sense of systems where infinitesimal errors in initial conditions grow exponentially over time, making any long-term prediction fundamentally impossible. Let us imagine the molecular cloud that gave birth to the Sun. If its conditions of temperature, density, and chemical composition had been slightly different, and here slightly means differences on the order of infinitesimal fractions that no instrument could ever resolve, the Sun might have been born with a marginally smaller mass, and this difference could have resulted in a substantially longer lifespan, or in a chemical composition of the solar system different enough that the rocky planets that formed had radically distinct proportions of elements. Life, if it arose in these altered conditions, would be unrecognizable to us, or perhaps it would not arise at all in this specific configuration, or perhaps it would arise on some other planet that in this alternative history accumulated the right conditions. The point is not that any of these alternative trajectories is more or less probable than the one that materialized. The point is that the trajectory that materialized was not the only possible one, and that the distance between possible worlds and the real world was determined by fluctuations so small they exist only on the boundary between what classical physics describes and what quantum mechanics makes fundamentally uncertain. And here we reach one of the most honest frontiers of human knowledge about the destiny of the universe. Predictions about heat death, about the last black holes evaporating into Hawking radiation, about the final silence of a universe in equilibrium, are extrapolations of physical laws we know very well under conditions we can test. But these laws were verified in a universe that is far from equilibrium, in conditions where gradients still exist and where matter organizes into structures rich enough for experiments to be possible. Extrapolating these laws to timescales exceeding the current age of the universe by factors of billions is not the same as extrapolating the trajectory of a billiard ball for a few extra seconds. It is an assertion that laws discovered in a specific context apply without modification in radically different contexts. And this assertion, however justified by mathematical elegance and the internal consistency of physics, remains an assumption the universe will never allow us to test directly. Quantum mechanics adds another layer of necessary humility. On extraordinarily long timescales, processes that quantum physics predicts as possible, but extraordinarily improbable in any observable time interval become, for purely statistical reasons, eventualities that any honest description of the future must deal with. Quantum tunneling, the process by which particles cross energy barriers that classically would be insurmountable, is so slow for macroscopic objects that its rate is described by numbers that make the current duration of the universe seem like an instant. But on sufficiently long timescales, even the tunneling of macroscopic objects, of rocks, of planetary cores, of any object that might exist after the stars go out, becomes a process that occurs. This means the description of the ultra-cold, nearly dead universe is not that of a perfectly static system awaiting its final dissolution, but of a system where even the silence is punctuated by rare and profound events, where quantum physics continues to produce surprises on scales no mind could possibly observe. There is a particular beauty in this combination of understanding and surprise. We understand the direction, we do not understand all the paths. We know entropy grows, but we do not know exactly when and how each specific gradient will dissolve. We can calculate that black holes evaporate and estimate on what timescale this happens, but we cannot know if there is physics we have not yet discovered that will modify this process in ways we do not anticipate today. The universe, in this sense, gifts us with a structure clear enough for us to understand its general narrative, and rich enough in detail that we can never be sure we understand everything that is happening. It is a strange and wonderful position to exist in. We are thermodynamic systems trying to understand the larger thermodynamic system of which we are a part. Every thought we formulate, every connection we make between concepts, every moment of understanding that emerges when one idea meets another and produces something that was in neither alone. All of this is a physical process consuming energy, producing heat and contributing by an amount beyond any capacity to measure to the growth of the universe's entropy. Understanding heat death is, in a sense, participating in it consciously. It is using the order that still exists to illuminate the direction in which all order is moving, and there is something profoundly quiet in this realization. Not quiet in the sense of desolate, but quiet in the sense of vast, like the silence that exists inside a very ancient forest, where every individual sound is absorbed by the expanse of space around it. The universe is moving toward an equilibrium that will take longer to reach than any number has the capacity to represent with intuitive clarity. On this journey, structures arise and dissolve. Stars are born and die. Galaxies meet and merge into new objects that have no precedent in previous generations. And all this abundance of forms and processes and stories happens within a tendency that always points in the same direction, that always follows the same logic, that always obeys the same fundamental principle. And it is in this single principle, in this tendency that simultaneously governs the cooling of a cup of tea and the final extinguishing of the universe's last stars, that resides something we have not yet fully named in this narrative, not because it is mysterious in the sense of inexplicable, but because its simplicity, once fully revealed, has the strange effect of making all the complexity that preceded it seem simultaneously more understandable and more surprising than it was before. Behind all this dance of gradients and structures and unimaginable timescales, there is something that fits in a single sentence, something physicists know and that any mind can grasp, and that unites in a single conceptual gesture the birth of a star and the silence of the universe in its final instant. This single principle fits, in fact, in one sentence, and the sentence is this: everything flows from what is concentrated to what is dispersed. There is no known exception to this rule. There is no territory of the universe where it ceases to operate. There is no time scale where it is absent. The heat leaving the cup of tea on the wooden table, the stars converting hydrogen into light for billions of years, the oceans evaporating and condensing and falling back onto the continents, the thoughts forming and dissolving in the neural networks inside a sleeping skull, all of these are local, temporary expressions of a single universal tendency that physics calls the increase of entropy, but which common language can translate simply as the walk from the concentrated to the dispersed, from the organized to the scattered, from the specific to the general. What makes this idea profound is not its complexity, but its scope. It does not belong to particle physics, nor to cosmology, nor to the thermodynamics of steam engines, although it appears in all these disciplines with the same force. It belongs to a layer more fundamental than any of these sciences, to the geometry of possibilities, to the pure counting of how things can arrange themselves. There is a mathematical reason why the universe walks in this direction, and that reason is simply that there are vastly more ways to be dispersed than to be concentrated. The universe does not choose disorder because it is lazy or indifferent. It falls into disorder because disorder is immensely more probable. It is like asking why a randomly shuffled deck of cards rarely results in perfectly separated suits. It is not impossible. It is simply improbable to the point of never happening in practice. And here we reach the deepest dimension of everything said in the previous parts of this narrative. When we speak of molecules, we are speaking of objects that move according to the laws of mechanics and interact according to electromagnetic forces, but whose collective history is governed by the statistics of possibilities. An individual nitrogen molecule inside a lung does not know it is participating in something called respiration. It does not know it is in a body, that this body exists on a planet, that this planet orbits a middle-aged star, that this star belongs to a spiral galaxy that in turn drifts slowly toward a great cosmic void. It simply moves according to the forces acting on it at that instant. But the collective result of countless molecules doing exactly this, each following its own local trajectory, is the emergence of something that only exists at scale, something we call temperature, pressure, flow, life. Emergence is perhaps the most astonishing phenomenon that physics contemplates without being able to fully explain. Simple rules, applied to many elements, produce behaviors that none of the individual rules contain. No water molecule is wet. Wetness is a property that appears only when many water molecules are together and interact with surfaces and membranes in certain ways. No neuron thinks. Thought is something that emerges from the activation pattern of billions of neurons in specific configurations, and no individual particle ages or dies. Aging and death are emergent properties of complex systems existing within an entropic flow. The universe, in this sense, is a system that generates emergent complexity from gradients. Where there is a difference in concentration, temperature, density, pressure, a flow can arise. Where there is a flow, a structure can arise that organizes and prolongs it. Where there is a structure that organizes flows, something can arise that reproduces, grows, responds to the environment. Where there is something that reproduces and responds, something can arise that learns. And where there is something that learns, there can arise, in rare and precious conditions, something that contemplates itself and the universe that contains it. We are that something. We are the part of the universe that has come to contemplate the universe. And the contemplation we perform, at this instant, on heat, death, and entropy and the final destiny of everything, is itself a manifestation of the entropic flow. The thoughts you form while hearing these words are physical processes dissipating energy. The understanding that settles in is a temporary form of order that the universe creates and will later dissolve. There is nothing melancholic in this. There is, if we want to find something, a kind of coherence that goes beyond what any cosmology can offer. The feeling that we are not separate from the process, but we are the process contemplating itself. Feedback loops play a central role in this story. There are feedbacks that amplify, making structures larger and more intense, and there are feedbacks that stabilize, keeping structures within viable limits. A star is a masterful example of stabilizing feedback. Gravity wants to compress it. Nuclear fusion produces pressure that resists compression. The balance between these two forces keeps the star in a stable configuration for billions of years. But when the nuclear fuel runs out, the stabilizing feedback collapses and gravity wins, and the star explodes or implodes depending on its mass, releasing elements in all directions, seeding space with the ingredients for future planets and future bodies and future minds. A planetary climate is also governed by feedbacks of both types. Albedo, the ability to reflect sunlight, creates stabilizing feedbacks. More ice means more reflection means less warming means more ice. But there are also amplifying feedbacks. More heat means less ice, less reflection, more heat absorption, more warming. The climate history of a planet is the narrative of these forces in tension, with entropy as the final arbiter that eventually dissolves all equilibria and leads the system to a state of lower gradient, lower difference, lower possibility of flow. On a molecular scale, the chemistry of life is a spectacle of cascading feedbacks, enzymes catalyzing reactions that produce the building blocks for other enzymes, proteins regulating the expression of genes that code for other proteins, hormones activating receptors that modify the metabolism that produces more hormones. The living body is a chemical conversation with itself, a biochemical narrative the organism tells without words, layer upon layer, cell by cell, molecule by molecule, in a complexity that defies any complete description but obeys at every step the same thermodynamic laws governing the cooling of a star. There is a profound symmetry between what happens inside a cell and what happens on a cosmic scale. In both cases, complex structures arise and are maintained as long as there are gradients to exploit. In both cases, these structures eventually dissolve when the gradients run out. In both cases, the dissolution is not a tragedy, but an inevitability inscribed in the mathematics of probability. And in both cases, while the structures exist, they accomplish something the dispersed, homogeneous universe could never accomplish. They create experiences, stories, memories, patterns of a richness that simple matter distributed uniformly cannot even imagine. At bottom, the heat death of the universe is simply the moment when all conversations end. It is the silence after all language. It is the rest after all movement. It is the state where the universe finally stops telling stories because there is no longer any gradient to fuel the narrative, no temperature difference to move an atom, no concentration of energy to build a structure, no asymmetry to exploit in search of work. The universe will have said everything it had to say. It will have created all the forms the gradients allowed to be created. It will have harbored all the minds that emergent complexity was able to produce, and then it will rest in a silence that is not empty but complete, not absence but fullness of a kind that no mind still warmed by stellar energy is capable of fully comprehending. This reconnects everything. The nebulae described earlier, with their gas clouds coagulating into protostars, were density gradients being exploited by gravity. The main sequence stars, burning hydrogen into helium for billions of years, were temperature gradients between core and surface sustaining the life of immense structures. The rocky planets, with their magnetic fields and liquid oceans and circulating atmospheres, were temperature gradients between hot core and cold space, generating the complexity necessary for organic molecules to self-organize into something called life. And life, with its ability to capture energy and create local order at the expense of more global disorder, was the most sophisticated gradient the universe ever produced, a gradient that came to contemplate itself. And now, at this instant, while the cosmos continues its slow and inexorable expansion, while the last red dwarf stars still flicker in some dark, remote corner of space, while black holes still spin in absolute silence, waiting for the last photons to dissipate before they themselves dissolve into warm radiation, you are here. You are in this moment. You carry in the atoms of your body the legacy of stars that exploded billions of years ago, so that the right dust would be in the right place at the right time for a water molecule to touch another and start the chemical conversation that eventually produced a being capable of asking what time is. You are safe. The universe has taken care of you since before you existed, patiently building over a timescale the human mind cannot truly grasp, all the necessary conditions for you to be here, breathing, thinking, feeling the gentle weight of your own body resting. You are part of this. You always have been. Every cell in your body is at peace with the universe because every cell in your body is made of universe. The same atoms that were inside stars are now resting with you, forming part of the slow, continuous rhythm of your breathing, the tranquil beat of your heart, the smooth flow of blood through arteries you never see, but that work ceaselessly to maintain the temporary and precious order that is you. While you rest, entropy continues its silent and gentle work. It continues spreading, dissipating, balancing. It continues transforming gradients into flows, and flows into structures, and structures into stories. Everything is in order. The universe is in no hurry. It has before it a timescale so vast that every night of human sleep is smaller than the smallest conceivable instant within it. And yet, every night of sleep matters. Every moment of rest is a participation in the rhythm of the cosmos. Let the body sink. Let thoughts dissolve like morning mist in light. You are safe. The universe takes care of you. The stars remain in their places. The galaxies continue their silent drifting apart. The black holes continue spinning in slow motion in the dark. And you, made of the same matter as all this, belonging to the same process as all this, rest now at the exact center of where you should be. Everything is in order. You are part of this. You always have been. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.